Okay, so let's have a look here. We talked, quick review. Quick review. We talked about the Hinge theorem last week, right?
Yes.
Remember what we said about the Hinge theorem? Okay, phones away, please. Phones completely away, like in backpacks, in pockets, put them away, please. So we said something about the Hinge theorem. We said that if we have two triangles that have two congruent sides, then we can make a comparison between the third sides based on the included angle, right? So let's find the two sides here based on this information that are congruent. So what do we know? AD equals 11, AC equals X, so we probably can't say anything about those, right? But BD equals 9, so the length of that segment is 9. The length of BC is 9. So those are congruent, right? All right, so we can do this. We can say, let's kind of color code this. So, whoops. So this guy is red and that guy is red. And we can do that, right? Vector. Emilio.
Let's go see what's going on. Moving on.
So those are congruent. Madison, what's another pair of sides in these two triangles, top and bottom, that would also be congruent? There you go. Good. They share a side. Very good. So we've also got side BA that's congruent to itself, right? And I could pull those apart now, right? So we said that the third side then is what we call the rubber band, right? So these are the that's sort of rubber band colored, I guess, orange, right? So there's a rubber band, and there's a rubber band, and we've got to determine which rubber band has been stretched more. Well, they give us some information. They tell us that the measure of angle DBA is 67 degrees, and the measure of angle CBA is 66 degrees. Okay, everybody's books up here, please. So what's going to be then, Ahmad, which rubber band is going to be stretched more? Well, I can't see your point. So say
Like like BG one.
B. Okay, well now let's get the Hinge theorem. Let's get squared away on the Hinge theorem, right? So with the Hinge theorem, we said that we had two boards in each triangle that were put together with a hinge. And then in another triangle, I've got the same length boards that are hinged. So here we've got the red board and the red board are the same length. The blue board and the blue board are the same length. And there's the hinges are right there, right? So we can, see what I'm saying? We can take the blue board and the red board and we can spread them apart at that hinge or put them closer together, right? And the opposite the hinge is the rubber band that's being stretched. So if the lengths of the red and blue boards are equal, right, then what do we know about the rubber bands here? Which one is going to be stretched more? Ruby, what do you think? DA. DA is. How come?
Because angle D is bigger than
Angle DBA is bigger than
CBA.
CBA, right? So that means that this hinge must be spread apart a little bit further. And because the lengths of the boards are equal, that means that the rubber band must be stretched more, right? So that's the Hinge theorem. Once again, if two sides in one triangle are congruent to two sides in another triangle, and the included angle is larger, then that means that the opposite side must be longer, right? Okay, so that's what the Hinge theorem tells us. The Hinge theorem tells us that this side right here must be longer, and there it must be shorter. So it wants us to come up with an inequality in this case, or an equation it could be, that's going to describe the restriction on x. So what's that tell us? Well, AD is equal to 11, right? So this is 11, and this is x. How do I come up with an inequality that's going to put some restriction on x then. What do you think?
11 is greater than
Yeah, right, 11 has to be greater than x, doesn't it, if that rubber band is stretched more. So 11 is greater than x, or another way of saying that would be x is less than 11, okay? That make sense? Okay, so this gives us an infinite set of values. Could x be 10? Could x be 10.9?
Yes.
Could x be 5?
Yeah.
Okay, but maybe there's a problem here. Can you think of a value of x? If x is the length of side AC, can you think of a value of x that really wouldn't make any sense? 0 wouldn't, would it? Because x is the length of the side in a triangle, and the length of a side can't be 0, right? That wouldn't make any sense. It wouldn't be a triangle. What's another value that maybe wouldn't make any sense? Yeah, like -1 or -2 or any negative number, right? You can't have a negative distance, negative length of a side in the triangle, can you? So what else must we probably also have to say here? What about x? X has to be some positive number, doesn't it? It can't be 0 and it can't be negative. So the other thing we'd have to say is x is greater than 0, right? So what we've got to do is find the combination of those two things. You know, where is that going to be true? Now, one way to look at this, and this is kind of what we did, I think we did this once before last week, but what we can always do is say, okay, well, where's going to be the intersection of those two inequalities? Where are they going to both be true at the same time? And then we could graph them both, right? We could say, let's take the number line, and let's make this 0, and let's make this +10, and let's make this -10. And let's just graph both of these inequalities. Let's make this one red, how about? If x is less than 11, what's that look like as an inequality if I graph that? What's that going to look like? X is less than 11. Do I put an open circle or a closed circle at 11? What do you think? Open, because it's not including 11, right? It's not less than or equal to, it's just less than. So we're going to put an open circle at 11. In which direction do I draw the arrow? To the right if x is less than 11. To the left, right? I want all the values that are smaller than 11. So it looks like that, doesn't it? There's x is less than 11. What about x is greater than 0? Let's graph that one in blue. So I'm going to, where does my endpoint go? If x is greater than 0. 0. Open or closed?
Closed.
Why would it be closed?
Because x is greater than 0.
Okay, but is it including 0? Because it's closed if it includes the point at 0. Does it say x is greater than or equal to 0? No, so it must be open then, right? Because it doesn't include the endpoint. It's just values greater than the endpoint, right? So we're going to put an open circle. And everybody gets that distinction, right? When we're graphing inequalities, and this goes back to Algebra 1, when we're graphing inequalities, whether or not we shade in or color in the endpoint just depends on whether or not we're actually including the endpoint. So whenever we're graphing a less than or equal to, or a greater than or equal to, we'd have a solid endpoint. But if we're graphing a greater than inequality or a less than inequality, we have to have an open endpoint because we're not including the endpoint, right? So what's this one going to look like? If x is greater than 0, our endpoint is at 0, are we going to the left or the right?
Right.
To the right, we want values bigger than 0, so it's going to look like that. Okay, well, where is the overlapping portion then? Where are both of those going to be shaded? Yeah, right? The part that's going to be overlapping is going to be this part starting here and ending there, right? So it's going to look like that. Now, how would I describe that region? X is greater than 0 and less than 11, right? Everybody see that? So really all we've done to combine these things then is we've recognized that this is our lower limit. So x is going to be greater than the lower limit and less than the upper limit, right? That's a compound inequality. It's an and inequality, isn't it? Because we're pinching x between the lower limit and the the upper limit, sorry. Lower limit and upper limit. So how do we think of that? Well, whenever we're going to write a compound inequality like that, that's going to restrict x both, with a lower value and an upper value, we just think of it like a number line. The x goes in the middle, and the lesser number on the number line goes on the left, and the greater number on the number line goes on the right. And that's how we'd enter the answer. Okay? That works, doesn't it? Right? Gives us all the values that x could be. We know it's got to be less than 11, but it also has to be greater than 0. Otherwise it wouldn't make sense. Okay? Let's try one more of those. One more of these. And then this is really the last stuff for chapter 5.
After this, so the test on Thursday.
Yeah. Okay, so what about one like this? Okay, same kind of thing, right? So first of all, we need to see if the Hinge theorem applies. Because if it doesn't, we can't really do anything about this. But let's see if it does. We're trying to see if there's some restriction on x here. So what are some sides that are congruent here again? If you look at the information.
BD, BC.
BD and BC, it says they're both 12, right? So those are congruent, aren't they? So we get the red board, which is 12, and the red board, which is 12. So I could say that they're congruent. And what else? What other side would be congruent? What other board could be the same length in those two triangles?
BA.
BA. Okay, so we'll make that blue. How about? Okay, and we don't know how long that one is, right? But it doesn't matter. We see that we've got a red board and a blue board that are the same length in each of the triangles, and so then the rubber band would be the third side. Right, so here are the rubber bands. Okay, how are we going to know which rubber band is stretched more? Where do we always look to see which one's stretched more? The angle, sure. So if angle DBA is 61 degrees, and angle CBA is 63 degrees, then which one's going to be longer? Yeah, AC's got to be longer, doesn't it? Right? Well, what are these? It tells us in this case that AC is 7x plus 3. And AB is 4x plus 6. Okay, but we know that this one is longer and that one's shorter. So what's the inequality we could set up then? What has to be true? If 7x plus 3 represents a longer side than 4x plus 6, Mallory, what do you think? What inequality could I set up there? What relationship? I say something is greater than something.
7x plus 3 is greater than
4x plus 6. Yeah, there you go. Perfect. So that tells us that 7x plus 3 is greater than 4x plus 6. Very good. Okay. We got to simplify that. how could we simplify that inequality? Remember what we said about, we talked about this a little bit last week. Doing algebra with inequalities is almost the same as doing algebra with equations. The one difference is what? Negatives. If we multiply or divide both sides by a negative, we have to flip the inequality. So we always try to set ourselves up so we don't have to do that, right? Which direction should I move the x's if I want to keep a positive number of x's? To the left. So how do I do that? Subtract 4x. Okay, and if I'm going to subtract 4x from the left side, it means I'm moving the x's to the left. Where am I moving the numbers? To the right. Okay, so Sierra, how am I going to get the numbers to the right? What do I have to do to both sides to get the numbers on the right? So I want to move, I'm moving the x's this way, which means I want to move the numbers the other way.
Subtract.
So subtract 3. Good. And look what happens. We get the right thing happening. I get the x's canceling on one side and the numbers canceling on the other, which is good. So how many x's do we end up with, Dean? If I'm subtracting 4x from 7x, I get what? 3x is greater than 6 minus 3 is 3. So what's the last thing I can do to both sides? Divide by 3. So we end up with x is greater than, well, 3 over 3 is 1, right? So x is greater than 1. Okay, good. So that's true, right? That's something that something that has to be true. Now, what else has to be true here, though? What else has to be true? Because yes, we know that this side has to be longer than this side, but are there any other restrictions on the sides? What did we say last time? That we can't have, like, could I pick a value of x, for example, that was negative 1,000?
No.
That wouldn't work. It wouldn't work in this case, but also it wouldn't work. Hey, Carrie, are you guys getting this? I'm worried you guys aren't getting this in the back. It looks like people aren't just totally focused up here. Okay, so just make sure. So that wouldn't work because that's going to give me negative side lengths for these side lengths, and that can't happen, right? So we also have to have the restriction that each of these rubber bands has to have a positive length. So how would I say that for, let's make this one red, this statement red. How can I say that that side length is positive? How would I say that? That the length of AD has to be greater than 0, right? So what does that become in terms of an expression then?
4x plus 6 has to be here.
Yeah, 4x plus 6, because that represents the length of AD. So 4x plus 6 has to be greater than 0, doesn't it? Okay, got to solve that. If I want to get the x by itself there, what are the 2 steps? Subtract 6. Okay, and then what's that going to do? Then we get 4x is greater than negative 6. Now there's a negative there, but what am I going to divide each side by? Now I can divide, that's positive. I can divide both sides by a positive number without flipping the sign, right? So I divide by 4, and I get x is greater than negative 6/4 reduces to what? Negative 3 over 2. So the same thing as negative 1.5. So that has to be true. Okay. What about down here? 7x plus 3, same thing, right? That side length, AC, has to be greater than 0, right? Because it's a side in a triangle. So AC is really, in this case, the expression 7x plus 3. So 7x plus 3 has to be greater than 0. Same deal, right? I'm just going to isolate the x. Subtract 3 and divide by 7. So what do I get when I do that? Well, 7x is greater than negative 3. So x is greater than negative 3/7. So I get these 3 statements that all have to be true, right? So I got to find the place where all of them are true at the same time. Well, let's look on the number line again and graph each inequality and just see what we get. So let's make that 0. How about making this like 2 and this like -2? Okay, so first of all, let's graph the orange one. X is greater than 1. What does that look like? What's that going to look like? Danae, if I want to graph the inequality, X is greater than 1, how do I graph that down here, that inequality of the number line? Open circle goes where? Graphing that. At 1, good. So we get an open circle right there at 1, and I'm gonna go to the left or the right with my arrow then, if X is greater than 1. To the right, very good. So there's one inequality that I get. Okay, what about the red inequality here? X is greater than -3/2. Emilio, what's that inequality gonna look like? So where's my open circle go? -3/2. Okay, so that's the same thing as -1.5. So wouldn't you say that's about right there, kind of? And I go to the right or the left? To the right. Okay, last one. X is greater than -3/7. So Hannah, what's that going to look like? Where's my open circle go? -3/7. So that's, pretty close to -1/2, right? So something like maybe like this right here. Open circle goes to the right or the left? To the right. Okay, so then the question is, where's the place where all 3 of those are shaded? Yeah, X is greater than 1, right? Does that make sense? So then the answer is just going to be that. X is greater than 1. That's all we needed. Doesn't that make sense? If you think about this, think about these 3 restrictions that we got here, these 3 inequalities. X is greater than 1, X is greater than -3/2, and X is greater than -3/7. When we're trying to come up with our solution to this thing, the one that's going to work in all cases, we have to just pick the one that's the most restricted, right? Doesn't it make sense that if I have values of X that are greater than 1, well, they're obviously going to be greater than a negative number, right? So that's the one that's going to work. But I couldn't just pick all the values that are greater than -3/2 because I could pick something like -1, which wouldn't work there and wouldn't work there, right? So the one that's the most restrictive in this case is the one that has to work in all cases. So that's our answer. Okay? Does that make sense? Okay? It's possible. It's possible. What would happen if we got an answer like this? What if we solved these 3 inequalities, and let's say we got these answers. What if we got the answer X is less than 1 for our red inequality, and for our blue one, let's say we got X is less than 0, and for our orange one, we got X is greater than 2. Is that possible? Can I have numbers that are simultaneously less than 1 and less than 0 and greater than 2?
No.
If I were to graph all 3 of those, what I'd find is there would be no place where they would all overlap, right? So what do you think the answer in that case is?
False.
False, yeah. Yeah, the answer, if you look at the instructions, if there's no solution, and are false, there wouldn't be any solution. No values of X would work. Okay, make sense? All right, we're done. That's chapter 5. That's a wrap.